Hi,
Hello?
Nolan.
Hi.
Philip, any questions on anything? How are the assignments going so far?
Okay.
No, Nolan?
Yeah, I actually have a few. I'm just waiting for my computer to restart, and then I will send them to you.
Okay. What about the other ones from previously?
Yeah, those are the ones I'm sending in right now.
Okay.
Because I have a few of those and some of the newer ones.
Okay. X.
I don't know where my fellow Trinity people are.
They'll be there. So who is going on spring break next week? Someone is.
Not us, I don't think.
I know there's someone who couldn't be here next week.
It's not me.
Actually, it might be us. I'm not sure. I'll have to check.
Yeah. There was someone who was going on some break and then something else. What about the week after that?
Oh, let's see here. 2 weeks from now, my spring break starts.
On the 23rd or that week?
I don't know the exact date, but I'll double check it right now.
And you have 2 weeks of spring break
Yeah.
or 1 week?
2.
Okay. So according to the MSON calendar, we are supposed to be on spring break till the 2nd of or the 30th of whatever the month is. I have the calendar up here. So we have the next class is supposed to be March 30th. Right? So I have the calendar says March 2nd week and then the March 30th week. So what I'm going to do this is I'm going to kind of post some readings for you to read. And then, of course, you have the assignments and the midterm to take during the break. Right? Schedule it with your proctors, and then you can take it anytime. So you'll have one week for spring break assignments and another week for the midterms, or whenever you can take that. Because it becomes a little difficult if someone is going on spring break. It kind of gets difficult to coordinate the schedules.
So what's the range of time for taking the midterms? You're saying it's like the 23rd?
So
week of
before you go on a spring break or after you come on the spring break?
Okay.
Because so every school has a different week. So within the next 2 weeks. Right?
Okay.
Then I'll email you when I submit the exams to the proctors, to Stephanie. Okay, any questions on anything? Can you see the the monitor?
Yeah, I can see it.
Yes.
So we know what hashing is, right? I mean, essentially, it's so there. Just to summarize what we did. Any questions on what we did so far? So go ahead. So we know how to. So there is something called the hash code that essentially the basic idea is arrays with some type of a way to maintain access to multiple items in the same hashed location. So we create a hash function and then modularize it to the size of the array we want, because hash function gives you a number between minus 2 billion and plus 2 billion. We modularize it to get a number between 0 and m, the size of the array you are trying to use. And then we can either have a linked list version of it, a separate chaining. So you have a hash location that each hash location has a little chain that goes from there. Something like that. And each hash location has a chain. And you want to make sure that the chain is approximately 3 to 5 in depth. So you can choose the array size based on the number of items you expect it to be in the hash code. Okay. So the other approach we thought was that you create what's called a linear probing. In linear probing, what we do is, what do we do?
You try to put it.
Go ahead.
All right, thank you. You try to put it in its space, but if you can't, then you just keep moving ahead until you find an empty spot.
Yes, right. So it's kind of like a parking a car. Like if you keep driving forward, and if you can't find a space at the end, then move back and start at the beginning of the block again. Right? That's what linear probing is. And if you're going to do linear probing, make sure that your array size is slightly larger than the number of items, because you need to have at least one spot per car. I mean, if you have too many cars and not enough spots, then it's going to be always you won't be able to work. You need to have some vacancies. The more vacancies there are, then the size of the the queue would be small, or the size of the search would be small. Right? So you can have a little larger than what you need, right? So when you have double the size, when your requirement is, if your size of the array is double the number of items, then your mean displacement is approximately 1.5, 3 over 2. So most of the time you would find it right away. If not, you may have to move one car space. Right? And when it gets full, the mean displacement turns out to be pretty large, pi m over 8, square root of that. Right? So that's a pretty large thing. I mean, you can, depending on m, you could end up doing a long walk. Right? So if you make a square root of m is still, I mean, you can square root of pi and 8 turn out to be pretty constant. It's a small number, but square root of m can be pretty large. Right? So try to make something that's larger than the thing. So this is essentially what hashing is. And there are different ideas based on hashing. Like, for example, there are some people try, of course, then the last thing we looked at was what is one-way probe hashing. One-way hashing is to take something and take a key, hash it into something. The difficulty in one-way hashing is that you cannot get back the key. and you cannot get back the key. So therefore, and we are not expected to get back the key. Most passwords are hashed like that. Of example, if you download something, have you noticed that when you download a file, they'll say after you finish downloading it, check the MD5 checksum, right? I don't know whether you noticed it, but we probably don't pay attention to it. But especially when if you're downloading a video file, who cares? You mess up a few bits over there, that's okay. But if you're downloading a program, the Linux operating system, which is pretty big, but then every bit has to be downloaded exactly. You can't have errors in it. So they hash it. They take the entire file, 600 megabytes of it, create a hash code for that, an MD5 checksum. And then what they do is, here it is insecure, that's okay. MD5 is not as protective as the other things, but that's okay because you're not really trying to hide it. They're just trying to make sure that. So when you download it, after you download, they'll say, okay, now run this program, download another program, rerun the hash code on this download you just did, and verify that the hash number looks exactly what it looks like. Right? So that's what it is. And then of course, so there are lots of hashing applications, digital print message digest and all that stuff. There are variations of it, right? There are things you can do with hashing. You can have, some people use double hashing, meaning you have two hash functions, and then you hash on the first one, and if that's already occupied, use the second hash function. So you kind of have, okay, let's try this hash function first. And if that space is occupied, let's put it on the other one. Instead of having to do a linear probing or separate chain, if we'll try the second hash function, maybe that space was vacant. So you can do something like this, double hashing, any of that stuff. So linear probing, right? How to delete and resize. If you think you're going to have too many elements now, you have to start with M, and you realize that, oh, M is not enough, I need to double it. You can say now the separate chaining kind of automatically accommodates that. The chain can grow as long as it needs to, but linear probing, how do we resize it?
Can we just, like wherever we have an empty parking space, can we just put more empty parking spaces at that location?
If you put more empty parking space, let's say you have an array, and then you kind of, okay, let's add more, increase the size to double the size. What happens is now you have a different hashed function, right? You have a different hashing array. So the option would be to take everything out from the first one and rehash it into the second one. Like pull everything out, like take everyone to now you have more parking spaces, ask everyone to take the car out and then bring it back again. And delete also the same thing. If you're going to delete something, and if you delete and you find that you have made a hole, you need to go around and make everyone go back and rehash everyone in that cluster needs to take it out and put it back. Because it could be downstream, it could be upstream. Everyone in the cluster has to now, that everything in that cluster needs to be pulled out and then rehashed back in. So it's a little bit of work in terms of deleting something, because you'll have to do a rehashing of things. That's essentially what we have for hashing. And we have for hashing, and there are other types of hashing, different types, right? Many versions have been studied, but the main idea is exactly still the same. So we kind of know basically what hashing is. So the next thing is network. But before I get to network, I just wanted to we talked about something last time, the HTTPS. Right? At least we need to have. So there are certain things that made a significant many things. For example, things we don't really appreciate. For example, the positional representation. That the identifying that we can place numbers and give them values based on numbers. Well, it's thousands of years ago, but it's a significant improvement. It made us do a lot of things that we couldn't have done. I mean, we overlook and say, oh yeah, someone is so easy. It's not so easy. Someone came up with that. Another thing recently, which has made a significant difference, is what's called the HTTPS type of work. So if you could not, we are doing it now. Everything is based on internet passwords and transactions, right? So transactions have to be extremely. If you are going to do an internet transaction, that's something which we don't. I mean, we kind of take it for granted again, but it's still so recent. Okay? That if you send your password hashed, or if you send your password, a person in the middle cannot open it. Right? Let's say, for example, there's A and B sending messages from A to B. Now there's E in the middle, eavesdropping. Right? Now the E wants to find out what the password or what you're trying to transmit. And how do we prevent that?
Encryption, I'm guessing.
Okay. We can encrypt it. We can take a password, we can take a key and say, hey, encrypt this message and send it to me. Right? So if I encrypt the message and send it to the other person, what would happen on the other side? So that's something called a key, right? So we need to use the key to encrypt and decrypt it. So that means we have to use a key, and B needs to get the key to A. B need to somehow find a way to get the key to A, because otherwise you can encrypt it. We have to use the same key. Like put it into a mailbox and mail it and say, this is what the key is. Get it from there. So the question, how do we get the key from B to A?
This is the thing with like the paints, mixing the paints.
Yes.
I think I know. You do like a one-way operation on a number, and then you send that number, and then the other person does their operation on the number, and then you do your operation on their number, and then you both end up with the same number. Kind of.
Right? Yeah. Yeah, but so you see the issue is how to get the key to the other person. Right? So because he needs to encrypt it. So one of the things that made everything possible it's called asymmetric keys, meaning you have two keys. Right? So if you lock it with one key, I'm going to call it the public key, you can only open it with the private key. There is this, right? So that you can, so if this is a one-way function that goes from this into something that's hashed, encrypted. But to break it, you have to use the private key to open it up. So you use one key to lock it, the other key to open. The best thing is that the key that locks won't be able to open it. So if you lock something, then you have to use the other key. You cannot use the same key to open that. So So that's a pretty good thing to do, because what I can do is if B is the bank and your A is the customer, right? The B can create its public and private key. Hey, this is the public and private key, and share that public key, right, with every customer. So the public key gets shared with every customer. So it has so everyone all the customers have access to the public key, including E. E also has access to it. Right? So everyone has access to the public key. Now A wants to do a transaction, right? A wants to do the transaction. So what would A do? A can send messages to B using the public key. Anyone can send messages to the bank using the public key. And that's not a secret, because you have your public key. Like, for example, so I am the bank and you are the customers. I'll post it on the board here. This is what the public key is. Anyone who wants to transmit the message can just encrypt it and put it back on the board. It doesn't matter, because even if everyone sees it, they can open it. Only I can open it. I have the private key. They can see the encrypted message, but you can't see the actual message. So it's easy for now that I have that. You can send it back to me, and I can take all I can look at the information. Now, how do I send things back to you?
I guess,
Use my public key.
yeah, you would give them
If I
my
have a
public
public
key, and you'd have your own private key.
So you also have to create your own public and private keys. So all the customers will have to create their own public private keys.
Well, there has to be a better way.
Yeah, right. But then that's a lot of work. Actually, the public key, private key, it's called the asymmetric key encryption. It's also very expensive. It takes a little bit of time to decode. It's not as fast as a symmetric key. So there's a problem, because what if I encrypt it using my private key and send it to you?
You won't be able to decrypt it.
But you can.
Oh, everybody else can though.
Yeah.
Exactly, everybody else can too, because everyone else has the same key, right? So this is now, if this public key, private key wasn't possible, your internet banking, internet transactions is completely out. You still have to walk to the store and buy things. I mean, we do everything on the internet. I mean, if 10 years ago you have to go and buy things, now you can sit at home and do everything. And that's because of this particular thing that made it possible. It's simple. It's not simple, but it's something that we don't pay attention to. So what you can do is you can do something like this. You know, the first I gave you the public key, right? All of you have the public key. So whenever you want to do a transaction, the first thing you do is you generate your own symmetric key, right? You don't have to make a public key, private key. So you generate your own symmetric key. So let's say, for example, so we have two keys, right? So I have a black, a red, and a green key, right? I have a red key. I generate a red key and a green key, and give you the green key to you. So what you do is, so you have the green key. You can certainly send me messages, because the green and the red go together. You can send me messages. But what you want to do is, the first message you send, generate a symmetric key. It doesn't have to be a asymmetric key. Generate a symmetric key, a blue key, and put that inside the first message. Right? So now I'm going to use your key. The first time you were using my key. right? My public key to send me the message. For all other transactions, I'm going to use your key with you. Right? Now only both of us know your key because you generated it, you sent it to me. So I know the person who has the key to open is the person who sent me the key originally. No one else has it. Right? So you generate what's called a one-time key, and you can throw it away after that. You don't have to keep it. Right? Every time you do something, generate a key and send it to me. Right? And then E in the middle cannot. Even if E gets the message, E cannot do anything because E doesn't know what the key is.
So from that point on, would you both use the symmetric key?
That's correct. Right? For the entire transaction, we'll use a symmetric key because we only both of us know what the key is. Yeah? And these are all called one-time keys because you don't want to use the same key again. The keys also have a timeout, like, okay, you can use this key. Right? Because you don't want people to kind of break into the key and come back and say what the key is, because the next transaction, even if you manage to break my old key, that's not the one I'm using right now. We have generated a new set of keys. Right? That's how the HTTPS works. So when you say HTTPS, that automatically creates that and says, hey, take my public key. So your web browser automatically knows that it needs to download the public key before it sends the encrypted message back. So it does all the transactions. Then the browser and the server will manage all that together. So the users completely unaware of the fact that the browser is doing all that for you. Right? You don't have to, because the browser and the server will negotiate and say, okay, that's what we want to do the future transactions and do that stuff. So the next question is, when A tries to go to the bank, why can't E pretend to be the bank? Why can E come and say, hey, I'm the bank?
Well, because they don't have the private key in the first place, so they can't unencrypt the symmetric key.
Right? But you need to download the public key first, right?
Yeah.
You need to download the public key. So E can pretend to be the bank and give you the public and the private key and says, hey, I'm the bank. This is my public and private key. You see the issue, the thing, right? Because you just type in and says, someone picks up the phone, you think it's the right person, but it could be E in the middle saying, oh, I am the right person you wanted to talk to. Hey, this is your private key. This is your public key, use it. How do you know B is the bank is who it claims to be?
Maybe we have somebody who both of us trust already holding all the public keys.
Yes. Right? So that's kind of what we end up doing. That's what digital certificate is. It's kind of like an ID. Like, for example, so you go to the DMV and get your ID. You prove that it's who you are to that person, and then he gives you the ID. You carry this ID saying, hey, I have been verified by this person. So there are these companies like VeriSign and different companies. So they actually verify companies and say, okay, you have to pay them some money to get the certificate. So what they do is they take your public key, do a one-way hashing, right? They do a one-way hashing and then put your public key and says, okay, now take this and give it to everyone else. It has the public key and the digital certificate from VeriSign saying this is an authentic key from Bank of America. So when you get the public key, you do the one-way hashing again, right? The standard procedure. So you do the one-way hashing again and verify that the hashing matches what's been stamped down here. Or alternatively, you can verify, send it to this place you know, and have it verified. Right? So that's the banks, all these people. Now, like sometimes you see a pop-up message saying that the digital certificate, this company does not have a digital certificate. Do you still want to trust it? In the Internet Explorer browser, has it popped up the message saying, "Oh, the digital certificate has expired"? Right? So the browser is programmed to request certain agencies. The browser is automatically programmed to request these agencies, and this is where you ask for digital certificate and nowhere else. And you can actually add them too, but by default it has a list of agencies that this is exactly where I'll verify it, and if none of these agencies can verify it, then your certificate I won't accept it. Unless the user clicks and says it's okay, don't worry, I know this person. You can still override it. You can still say yes, accept. You can still say, yeah, that's okay. I don't know, this message keeps popping up. I don't know what it means. I'm going to click okay anyway. Right? So I mean, what else can you do? If you don't click okay, you can do the other thing. Right? So you click okay, and that's essentially the browser trying to tell you that this thing is presenting me with an ID. Either the ID has expired or it does not come from a place I know I can trust. It doesn't come from a trusted source. Right? This digital certificate it presents does not come from a trusted source. It's not like from the DMV or the passport office. It's he claimed someone from his neighbor said, I know this person who's lived here right next to me for the next 20 years. And you don't know who the neighbor is, so they each validate each other. And that's what happens when you try to do that. So the encryption, hashing stuff, all that stuff is pretty useful. And it is. Without that little thing, you could not have done what we are doing right now. To be able to log in and it's made a tremendous change in the whole world commerce. Everything we do. The ability to be able to do public key, private key encryption. Right? Encryption was fine. There had been encryption schemes from beginning of time. Like people have tried to put things into Caesars. There are different names. The public key, private key that you can only lock with one and open with the other is pretty unique. Right? So the algorithms are pretty straightforward, but so what makes the key more difficult is not the algorithms. The algorithms everyone knows. Everyone knows how to create public key, how to create private key. It's just the key. So that's the other thing that's beauty of it. Now, if everyone comes up with their own algorithms, too many algorithms, right? It's not like there'll be like millions of people having their own secret code. It's not the code that's difficult. It's the brain. So all of us use the same algorithms to create them, but it's the numbers. So they start with some prime numbers. They start with some prime numbers and then come up with the algorithms. And it's just that guessing the prime number is difficult. There's no known way of no quick way of guessing what the initial number was, other than the brute force way. Right? So it's just I know how you're doing it. I just don't know what you put into this. It's kind of like I know you mix two paints together. I just don't know which paint you mixed. Right? And everyone is going to mix two paints and take a neutral and give it. Right? So they'll paint it, mix it, and send it to me. I just don't know which colors you mixed. Okay? So that's the beauty of IDEA, that it's very simple. It's very easy to know what the algorithms are. but difficult. So the difficult part is not in the fact that the prime numbers, prime factorization, it's based on some prime numbers. And what's the known prime number? Now you know that how many prime numbers are there?
Well, infinitely many.
How do you know it's infinite?
Infinite number of numbers, so
So that doesn't mean that there has been infinite number of prime numbers.
that's true. Yeah, the prime numbers definitely get less common as you go, but they have to still increase. But
Yeah, it is certainly less common, yes, but how do you know it's infinite? And what is the known prime number right now? How large is the known prime number?
is it like I'm not sure.
To like 57 million.
So like 20 million digits?
Yeah, about
Right.
17
million digits, yeah.
Yeah, right. It's right. So divided by 3, because anything that's 2 to the power something divide by 3. 57 million digits, and you think there are more than that?
Probably.
Well, there are, and we'll prove it.
Sure, but
Yeah, we'll prove it, and the proof is very easy. So let's assume that there are actually fixed number of prime numbers n. It can be very large, but n. So now, if with this assumption, if there is the number of prime numbers is fixed, then can I line up all of them? P1, P2, P3. Right? I can just list them, all of them, right? It's going to be a large number, but certainly I can list it. Well, now I'm not going to list it. I'm going to multiply all of them times. Right? Do a times operation on all of them. Pn. Now that will give me some number. Right? So certainly I can list all the prime numbers and multiply them and create a resulting number. Add 1 to this. Right? And I claim that this is a prime number.
Why?
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 Okay. Divide it by any number. What will be the remainder? If I divide it by P2, P1, what's the remainder? What is this big number what is M divided by P1?
It'll be some number, but no remain. Wait.
No, plus 1. Plus 1. Because there's plus 1. So this side has a factor P1. So you see all these numbers on this side are not factors. So if I divide by P1, I cancel the P1s. Right? So if I had divided M by P1, there would be no remainder. Because M was a product of all the numbers. But if I divide M plus 1 by P1, there would be a remainder.
So are you saying that the product of any two prime numbers plus 1 is also a prime number?
No, I'm not saying product of any two prime numbers, right? So I'm saying if you certainly the product of any two prime numbers cannot be divided by any of those two numbers. Let's say, for example, you take the prime numbers 3 and 5, right? So 3 and 5 gives you 15, but if you add plus 1 to it, 3 and 5 will not divide it. Because 3, so go ahead,
I was going to say, yeah, I understand.
right? 15, 3 and 5 will divide it. But 15 plus 1 will have a remainder of 1, whether you divide it by 3 or whether you divide it by 5.
So why can't they find more prime numbers in this way?
Yeah, but those are, they know they exist. They may have missed many. Now you convinced with my proof?
Well, with that 3 times 5 example, that doesn't work because that's
Why
just
not?
16. Because that's
Yes,
just
but
16.
Yeah, but I said it
Oh.
won't. You cannot divide it by 3 and 5. You cannot divide
but-
this number by 3 and 5. But you can divide by 2. Right?
Yeah.
So
Yeah.
what I'm saying is, now that you have listed all the prime numbers, this M is not just 2 prime numbers. This is all the prime numbers we know that exist.
Yeah, I think that works.
So is it a prime number? M plus 1 is a prime number?
I think it is.
Yeah, I think so.
Convince yourself, or just tell me why it doesn't work. So
Well, with your 3 times 5 example, if we multiply 3 times 5 and we get 15, we add 1. We can
Yes.
divide it by 2. We can divide
Yeah.
16 by 2, but then we multiply 2 by 3 by 5, so that we can't divide 2.
exactly. So it's going to be 2 times 3 times 5. What's that number?
30 plus 1 is 31 is a prime.
31 cannot be divided by 2, 3, and 5. That's what I'm claiming.
That's right.
Right? Because 2 is a factor. So if I line up any set of prime numbers, if I line up all the prime numbers and the ones I assume that it is finite, I assume that they are finite. So I go up all the way to the last number, I multiply that, and I get my number M. I'm claiming that M is not a prime number, but M plus 1 is.
Also M minus 1, right?
M minus 1, yes, right?
Okay. I'm looking at a list of prime numbers, and like if you start at the beginning and you multiply 2 and 3, then you get 6. But then if you subtract and add 1, then you can get 5 and 7, which are the next 2 prime numbers. And then if you do 2, 3, 5, you get like 30, and then 29 and 31 are prime numbers.
Yeah, but it's not all prime numbers come in pairs, but
Right,
many
you'll
of them
find
do come. Many of them do come in pairs.
You don't find all that way.
Yeah, not all of them. So usually a prime number has a pair also, twin primes. Like if you find one, you can look on the other side and find its twin sitting there. So that means my initial assumption that the prime numbers is finite is wrong, because every time if you tell me finite and make a list, I'll multiply them and show you that there's one more. Right? So it's proof by contradiction. I assume that it is finite, and then I show that it is not, because you can list as many as you want, and I'll show you one more than that. Right? So it's a very old proof, but it's been there for a long time and very simple to show that. So it's the prime numbers that makes it difficult. For example, nowadays people use encryption numbers. Now we say if you're using a 128-bit encryption, then that means you're using a prime number that's about 128 divided by 3. It's about a 50 digit prime number. Right? So the question is to guess that 50-digit prime number. And that's why it's a pretty long number. If you're going to use a prime number that's 50 digits long, and you need to be able to guess it, that's a pretty number. It's going to take a long time to guess it. It still can be broken. So now some of these agencies, like the government agencies, they actually use prime numbers that's 2000 digits long. Their encryption is not a 128-bit encryption. That's an 8096-bit encryption. So that you have guessing a prime number that's 2000 digits long. I mean, because they're concerned about not that you don't break it today, that you don't break it for the next 100 years. Because if you break it 10 years from today, that's still bad for me. Right? So I have government transactions, some important transactions that sometimes, because people capture the transaction, they say Eve in the middle still can capture the transactions and record it. The Eve cannot break it right away, but there's nothing that says Eve cannot capture it, put it onto a drive, take it home, and work on it for the next 2 years. Right? So what if Eve breaks it 2 years later? Is that damaging to me?
It maybe depends what the data is.
Yeah, it probably is, because if I have lots of plans and I have done these things and I've been saying these things, and they can go back and say, oh, you lied 2 years ago, because I can show you all your transactions and you use credibility right there. And then they can come back and come after you saying, well, you did these things 2 years ago, or 10 years ago, or 50 years ago. So the fact that they can capture the transactions, take it home and work on it for the next 25 years and come back and claim that everything I did and break my secrets is still wrong for me. Right? So you want to come up with prime numbers that doesn't really get broken in the next century or so, even with the fastest machines. So that's a little quick thing about finishing up the hashing and stuff like this. But there's one more thing I actually overlooked last time. So we looked at number representations, how to represent integers, how to represent floating points, right? So there are different ways. One is to, so we had this positional representation. So if you have 32 bits, integer has a way of representing numbers, and floating points use the same 32 bits but break it into 2 segments, one for the exponent and one for the mantissa. Right? So so you write it as a long binary number and count how many bits it's away the decimal point is, and then represent that as a second number. Right? We did that. What about negative numbers?
You just need one bit, 1 or 0, like 1 would be positive, 0 negative, or something like that.
Right? So you can take one of those leading bits. Can I do that? Can I take one of those leading bits, like the first bit? So if I have 32 of them, I can take the first bit and say, I'm going to use that as a sign bit. Right? A 0 would be positive. A 1 would be negative. Right? That's almost true. And that's why the range of an integer is from minus 2 to the power 31 to plus 2 to the power 31. So it's really not going all the way to, it's not using 32 bits because it's using the first bit. It's only using the 31 bits for the number and the first bit for the sign. Right? But it's not entirely true, because let's take a small thing and say, let's try this out. Let's take 3 bits, or let's take 4 bits. Right? If you take 4 bits, then what's the range of the numbers? If you're going to use only positive numbers, what do we get? The 4 bit is going to be 0, 0 like that. right? And there, what's that number 0? What's this one?
1.
1. This
Right. That's 2.
2.
So does it go up to 15?
Go up to, well, let's see what I want to do, right? So I can go up to 15 if I have to, but what if I decide to use the first bit as a negative number?
Mhm.
Then I don't have the option of going up to 15, because then I have the this is 0 1 0 1, that's a 5. 0 1 1 0, that's a 6. 0 1 1 1, that's a 7. Now if I want to use the first bit, so this is going to be the other thing, right? So minus 7 would be 1 1 1 1. If you use the first bit as the sign bit, so this is the 7 part of it, and that's the plus part of it. And here this is the 7 part of it, and that's the minus part of it. So you have two options: either go from 0 to 15, or go from minus 7 to plus 7. What do we want? Minus 7 to plus 7. Depending on what we choose, how we choose the first bit to be used. If you use the first bit as a sign bit, well, then you have the option of representing negative numbers. If you don't use the first bit as a sign bit, then it goes all positive only. You can go from 0 to 15. Now, if you have done C programming, you would have noticed that they have a thing called int and an unsigned int. Right? So unsigned int is telling the compiler that, hey, I don't want to use that as a sign bit. I'm only using it positive numbers. Because if you're counting things, well, there's no negative. I mean, if you're counting the number of things, then it will always be unsigned. Okay? So that's what's called sign magnitude representation. Because usually the first bit is the sign bit, the remaining bits are the magnitude, sign magnitude representation. But if you notice, there's a problem. So what is this number? What is the first number here? So of course I know that what is this number? If this is 5, what's 1105? 1.
Negative 5.
Negative 5.
Well, there's going to be 2 zeros because there's no negative 0.
Exactly. That's a positive 0, that's a negative 0. Which 0 is greater than what? Is negative 0 less than the positive 0?
No, they're the same.
They're the same. Right? So that kind of complicates things when you have two representations for the same number. Right? So what they do is what's called a 2's complement representation. So essentially what they do is that instead of doing it like this, they just still go, the positive numbers go the same way. The negative numbers go like this. It starts off with that, and then we're going to write all the representation that's possible. Exactly the same thing we do. That this goes from 0 to 7 all the way, and then when it reaches the next, it starts at negative 8 and comes down to negative 1. Right? So if you keep running, or if you keep changing the bits all the way to the top, after 0 1 1 1, the next number, which is 1 0 0, is negative 8. This is positive 7, that's negative 8. And then comes down. So everything kind of gets shifted by a little. This is what's called 2's complement representation. So now we don't have 2 zeros. It had 2 zeros. Right? So if it is a 32-bit number, so it actually this time the range is from -8 to +7. On the minus side, we have an extra number. On the plus, because 0 takes up one of those positive, so-called positive numbers, the negative side has an extra number. The positive side has one less number. So this is why if you look at the anything, if you have n bits, then it's -2 to the power n minus 1 is the least negative number. And on the most positive number, it's 2 to the power -1 minus 1. Right? So it's 2 to the power -1 number minus 1. If you have noticed it, it's always one number more on the negative side and one number less on the positive side. And that's 2's complement. So it rolls over, like it kind of goes all the way to the, if you're doing this, it rolls to the maximum. Where's my cursor? It goes to the maximum, and then suddenly it goes down all the way to the most negative number and starts climbing up. Right? It reaches the maximum, like 1, 1, 1. As you keep rolling the numbers, it reaches the maximum, and then it drops down to the most negative number. And then if you keep rolling these numbers, it reaches back to -1. So the -1 is always all ones. It doesn't matter what you use. -1 is always all ones. 32-bit, 64-bit, it doesn't matter. -1 is always 1. There's only one complication here which we have to we haven't looked at is, but how do you know like if I give you a number like -5, tell me the binary representation of -5 quickly without writing all of them out. So which one is -5?
It's going to be the 3 because it's like 8 minus 5 is 3.
So we know that the first one is -8, right?
Right.
So this is going to be -7, -6. That's -5.
Yeah.
Right? We have to count down. Is there a faster way? Yes, there is one. And what you do is you take the +5. This is +5. Where's my right? Take the +5. Take the positive representation of it, 0, 1, 0, 1, and do what's called a complement. Invert all the 1s to 0 and 0s to 1. So you have what, when you complement it, what do we get? 1, 0, 1, 0. And add 1 to this. Then you get 1, 0, 1, 1. Right? So if you want to determine what the negative binary representation of a negative number is, find out its positive representation, complement the bits, and add 1 to it. Well, we can keep talking about it, but we need to go. So my question is, so what I'm going to make this available, I mean, if you tell your friends, tell them too, that I'll email them, that next week and the week after, I am still available. And I'm not on spring break. I just have a difficulty coordinating the different schools, and I don't want to keep repeating what I did. Like saying, oh, today someone missed the class. And I can't really teach something if they're not going to be there. It's not fair to teach on a spring break. So if anyone needs to meet with me, email me and says, let's go through this, let's do something else, right? Let's start anything that you want. I'm still available for the next 3 weeks. Actually, that's the next 2 weeks. Then I take a spring break. Right? So anytime you have any questions, you're still open to email me. Right? If not, go ahead.
You're just saying, all right.
Okay. Leave it.
Yeah, if not, we'll meet on the 30th of March. That's a long break now. Don't forget anything we learned.
Okay, sure.
All right? Put it into long-term memory.
All right.
Okay.
Thank you.
Thanks so much. See you later.
You're welcome.
All right, thank you.
Thank you.